Hello everyone, my name is Fayssal El Masdouki. I will first thank this event to give me the opportunity to present my PhD project. So my project is a collaboration between University of Science Rabat and University International Rabat, supervised by Professor Mohammed Loulidi and Professor Mohammed Balli, with a team composed by Professor Benyoussef Abdlilah, Professor Kenz Abdallah, and Professor Mounkachi Omar. So the subject of my project is to study the stability of the hydrogen in the magnetocaloric material, lanthanum, iron, silicon, hydrogen. So the first or principal motivation about my material is his magnetocaloric properties for cooling application. So like we know, the old technology about cooling is based on gas cooling. This gas is so negative for the environment. So research wants to replace this gas with magnetic material. In our case, the lanthanum, iron, silicon have a good potential for this kind of application. So here I present the elements of my material. So the material have a lanthanum, a rare earth, the iron, a transition metal, the silicon, a semiconductor, and the hydrogen, a non-metal. The magnetic character is for the iron with ferromagnetic character. The structure of my material is the cubic complex structure of NaZn13 with 120 atoms in the unit cell. The material have two kinds of iron. The first one is the icosahedral structure, and the second one is into the first one. So for an application in cooling magnetic, the material should have a high isothermal entropy change and a high adiabatic temperature change and the Curie temperature beside room temperature. So like we see in this table, the material have a good magnetocaloric properties, but the Curie temperature remain low for cooling application. In this case, we add the hydrogen into the material to increase the Curie temperature. So the material is usable for cooling application. But the major problem of adding the hydrogen into the material is the diffusion. So the material become inhomogeneous with two regions. The first one is condensed by the hydrogen and the second one without hydrogen. The impact of this diffusion is for the Curie temperature. So like we see here in this graph that the Curie temperature have been split by two temperatures, and that is so negative for cooling application. Many solutions have been proposed like doping by the manganese or saturate the hydrogen into the material, but this kind of solution decrease the magnetocaloric properties, and the material remain useless for magnetic cooling. So in my PhD project, I will study the mechanism of the diffusion of the hydrogen into the material. I will use the physical simulation methods like the density functional theory, the kinetic Monte Carlo, and the molecular dynamics. So my first work of my PhD projects is to study with the DFT the properties about the material and his hydride, to extract the impact of the hydrogen into the material and his stability. The first result that I have extracted is the density of stage, the anisotropy, and the electronic density. So here I present the density of stage, so we can see that the two materials have the same character, and it is the metallic character and the ferromagnetic character. And we can also see that when we add the hydrogen into the material, the density of stage have slightly changed. So the second result that I have extracted is the anisotropy. So we can see that the two materials have magnetic anisotropy, and we can also see that when we add the hydrogen, the AZ axis magnetization and the hard axis magnetization have been changed the direction. The last result that I have extracted is the charge density. I extracted the charge density to investigate the bending of the hydrogen into the material. So like we see in this picture, the hydrogen is bending with the iron without the silicon. So when the silicon is beside the hydrogen loses some bend. So we can conclude that when we increase the concentration of silicon into the material, the hydrogen loses some bands and decrease his stability. So thank you for your attention.